All right, so hello everybody, welcome to Quantum Computation, PH870. We are on lecture 9 today. And so in the first 7 lectures, it was mostly mathematical preliminaries. In lecture 8, I started talking about quantum gates. We discussed the CNOT gate, and we saw that the CNOT gate is what is known as a control NOT. So there is a control qubit, and there is a target qubit, and the target qubit is the components are swapped if the control qubit is 1, otherwise it's left untouched. Of course, the most important thing to remember in all of this is that the input to your circuit in general is an element of the tensor product space H1 cross H2, which is much larger than either the space H1 or the space H2 by itself. Okay. Okay, so now let's see. So today we'll talk about, so we'll continue talking about some things. So one important aspect about the CNOT gate is that it is part of what is known as a universal set. Of gates. So there is CNOT and some combination of single qubit gates. And if you have these gates, then together, okay, what happened? Then together they form a universal set of gates, which means that you can construct any gate from the elements of this set, right? So I mean, it's just like the NAND gate is universal for classical computing, the same way this is universal for quantum computing. Of course, these are not the only possible choices. There can be different sets, different possible sets of universal sets of gates. So okay. Now, let me talk about something that we will be using all the time, and this is called the computational basis. So let me introduce what this is to you. Okay, so the computational basis, let's work with 2 qubits first, okay? So for 2 qubits, our state can be written in this way, right? So you can view each one of these, right? So you can see that this is the binary representation of 0, right? And this is the binary representation of 1, 2, and 3, right? So we can also alternatively write these states as 0, 1, sorry, beta 1 plus gamma 2 plus delta 3. And I'll put a little bar over the number to indicate that you know, this is like a logical assignment, right? So this is what is known as the computational basis. So if you use 3 qubits, for instance, right? If you have 3 qubits, then what will be your allowed right? These will be your basis vectors, and there will be how many? There will be 8 of them, right? 8 basis vectors. And once again, you can take these basis vectors and map them to the numbers 1 to 7. So this will be 6, sorry, 6, and then 1, 1, 1 would correspond to 7, right? So the way you can write down a state in this computational basis is as follows. The notation becomes a little bit simpler, right? N is equal to 0, and it goes up to either you can write it as n, or you can write it as 2 times d minus 1, where d is the total dimension, and then you can write some coefficient, and then you can write your state vector simply as the vector n with a bar on top, right? Okay. Now, so we'll be using this all the time. This is called the computational basis. But there are other choices of basis also, right? Obviously, there are an infinite number of different bases. So one common basis that is we'll be using often is this, which is so this is one set of basis vectors, but you can construct similar sets of symmetric and anti-symmetric combinations. So for instance, if you have 2 qubits, right, you could have a symmetric combination like this, right? I'll call this a plus state, and then a minus state would be something like this. Okay, so you can have symmetric and anti-symmetric combinations of this form. Okay, so now let's talk about one more gate, which is so this is a circuit actually. It consists of a sequence of gates, and it's the swap circuit. Okay, so what is a swap circuit? Well, if you have two qubits, okay, let's say the first one is in the state phi 1 and the second is in the state phi 2. Then what does the swap do? Well, it does what the name suggests. It exchanges the two qubits. Okay, if I write it in the tensor product notation, an arbitrary state of this 2 qubit Hilbert space can be written as you can write it as C ij I tensor j, right, where I is equal to 0 and 1 and j is equal to 0 and 1. So please convince yourself that this is exactly the same as this earlier expression. Okay, I mean, those two, this expression, they are both one and the same. All right, so what the swap circuit will do, right, when it acts on psi, it will basically take these coefficients and it will exchange them. So you will get a new state psi prime, which you can write as C prime ij I tensor j, where C prime ij is equal to CJ. All right. So for instance, if your input state is 0 tensor 1, then your output state is just going to be 1 tensor 0. Okay, and please note that this is not to be confused. Do not confuse with the CNOT gate. Okay, the CNOT gate is a single qubit gate. What it does is it takes the 0 state and swaps it with the 1 state, but on the same qubit, right? The swap circuit is exchanging the state of 2 different qubits. All right. So let's see how this works now. Okay, and so a little bit of space is needed here. Okay. So basically what it is, it's a array of 3 CNOT gates like this, right? So each one of these individually is a CNOT gate, right? So this is 3 CNOT gates, and so we can represent this as follows, right? So again, let's say this is A and this is B, right? So we can look at what happens step by step, right? So the first step is, after the first gate, what is the result? The output of the first qubit is just A, and the output of the second one is A XOR B, right? Now, what is happening in the second step? In the second step, we have exchanged the control qubit. This is the control qubit in the first step, but now this is the control qubit. So we have exchanged the control qubit. And so your output is, so let me actually make this a little bit bigger. So, okay. So now our control qubit is the second one. So the control qubit remains untouched. You get A XOR B. And here what you get is you get the XOR of both of these inputs. So you get A XOR A XOR B. Okay. And then again, the same thing happens. You get A XOR B. And then here, what do you get? You get A XOR B XOR A XOR B. Okay, so this looks complicated and like, well, what does it evaluate? What does it work out to? And what it works out to is that this is B and this is A. Okay, so I will leave that as an exercise for you to work out what happens. Actually, it's not very difficult. If you take 2 bits and you ask what is A XOR B, and then again XOR with the first or either one of these, you can show that this is equal to B. And similarly, if you have B XOR B, this will be A. Okay. So that tells us that this guy is going to be B, right? And then here, what we have is in this last output, we have A XOR B, and that is going to be A. So the exercise for you is to prove that okay. Does anybody know how to do this exercise? So this circuit can be written as follows. It's represented in short by this diagram. And so this is the swap gate. Okay, so it's a product of 3 CNOT gates. Now, what if you want to write down explicitly the quantum state that results as an application due to an application of these 3 sets of gates? Okay, so first of all, let's look at how you would write down the result of a single application of CNOT. Okay, so now CNOT is a 4x4 matrix. And okay, and so we will call this, we'll represent it with some symbol R and indices ij, right? And your input state is something like this, let's say, right? And just to clarify, I can write this tensor product in various ways. Okay, I can write it as this, or I can write it as I tensor D, all within one ket. They are all they all mean the same thing. Okay, so how can I write down psi out, which is what I get after I act on psi in with this Rij gate, right? So let's see. Right. So we should actually think of this CNOT of this CNOT gate. So okay, let me again introduce some more notation. If you have an operator O which acts on your Hilbert space, right? So what does this operator do? It acts on some state psi and gives you some other state psi prime. Okay. Now, so if you remember, operators can be written in terms of states, right? So I can have something like this. Let's say I have a basis of my state space. Okay. And what are my basis elements? Let's say these are my basis elements. All right. Then I can take any operator and okay, so this is my, you can call it a lemma or a claim or whatever, right? This is the statement that if you have a set of basis vectors, you can write any operator in this form. And what would be the action of this operator? So for instance, if my state is something like this, so I'll use, oops, again, I'll use ck phi k. So this is my state. Then what is the action of my operator on this state? I'll take my expression for the operator, which I have written earlier, phi j, sum over ij, and I'll act on psi. So what is psi? Ck phi k, and there's a sum over k also. Okay. Now ck is just a number, so that comes out, and then you'll be left with ijk, ij phi I, and the inner product of phi j and phi k. Right? What is this? This is going to be delta jk, right? And then you can take the sum over k, for instance. So I'm sorry, this should not come outside of the sum. It can come outside of the, it can come over here. So if you take the sum over k, for instance, you will be left with ij, oij, and one second, oij acting on cj times phi I. Okay. And I can write this and in the following way. I can write this as sum over I of ci prime phi I. Okay, so this is my original state psi, which I have written as a superposition of my basis vector. Then I take an operator and I act on this state. Right, so here I've just used some linear algebra manipulations. Right, and what I'm left with is an expression for my final state, which is the result of my operator acting on my state. And the final state is given in terms of some set of coefficients ci prime. Right, and you can see what is the relationship between ci prime and ci, the original set of coefficients. Ci prime is equal to oij times cj. Okay, so this is the relationship between, this tells you how an operator transforms a state, right? So when I have this expression here for my CNOT matrix, right, what you should think of is that there is, it's what this Rij corresponds to is the following, that if I want to write CNOT, I should, well, I'll continue over here. So for instance, the CNOT operator would be written as Rij I, sorry, not tensor, outer product j ij. Okay, and please do not get confused between this tensor product of two states and the outer product of these two vectors. Okay, these are two, they are distinct objects, so please keep that in mind. So this is my CNOT gate, and Rij is this matrix, and this matrix is in this case is represented by has these elements. Once again, you have to keep in mind that the matrix elements depend on your choice of basis vectors. Okay, so if I change my basis vectors, my matrix elements will also change. Okay. Oops, actually, I made a mistake. Yeah, CNOT is a 2-qubit gate, no? Yeah, no, it's fine, it's fine. You just have to be careful. What you mean by a basis vectors? So these basis vectors I and j, what are they? Right, I and j. They are the basis vectors of your 2-qubit Hilbert space. Okay. So I runs over 0, 0, 0, 1 till 1, 1, and similarly j runs over those. Okay, it's important to keep that in mind. So now I can ask, what happens? How will I write down the matrix representation of this swap gate, right? So what is happening is I'm taking my initial state and I'm acting on that with one CNOT, right? And then CNOT, but in the opposite sense, right? So what is this opposite sense? So if I write down the CNOT matrix, if this is my CNOT gate, right, and I write down the matrix elements as Rij, then what should be the expression for the matrix elements of this guy, right? And so here this would be I and j, right? I and j. This would be, let's say, some R prime ij, whose matrix elements are just the transpose of my CNOT gate, right? Because if you take the transpose, you switch the two indices, and the first index is acting on the second qubit, the second index is acting on the first qubit. All right. So if you take the transpose of this of CNOT, what will you get? Well, let's see. One second. No. It's not just the transpose.
Sir, I don't understand how you can so easily.
My bad. No. 1 second. I'm wrong. This is not the transpose. Let me just correct my error. Let me write down explicitly the matrix elements of Rij. The matrix elements of Rij will look like this. Yeah. So it's not simply the transpose. Go ahead. Does this clarify your doubt or not?
Yes, sir.
Yeah, this is what you're going to say, right? Yeah. So I was wrong. My bad. All right. So what is this swap gate now? The swap gate is a product of these three operations, right? You start with a state psi. You act on this state psi, and so let's say the state psi has some coefficients. So it's given by some coefficient Ci or Cj. You act on it with one CNOT, right? So you multiply Cj with this matrix Rij, but then you act one more time with this inverted CNOT, so this matrix R prime, but now you have to sum on the second index, and then one more matrix but this time again the CNOT one. So R, K, and here let's say something like L. And so this is, let's call this C prime L, right? So our input state, so let me take that. Copy. So our input state is psi, our output state is psi prime, and so this is written as CL prime sum L, and this is written as sum over CI prime I, right? And again, please keep in mind that I and L, they are again elements of the same set of basis vectors, right? We're working this computational basis, that has not changed. So again, exercise, evaluate the matrix for swap. Okay, so it's just a 3 matrix multiplications, and they're not typical, they're not too hard. Okay, all right, now so this is an example of so we have introduced a control NOT gate, but in the same way we can generalize the control NOT okay. So the controlled anything basically, okay, or the controlled U. So what is, how do we write this? How do we do this in a circuit? Well, we have one line which represents the control qubit, and then we have a box which represents our U gate. And so this U gate could be acting on any number of input qubits, okay. Like this. And so this is our control qubit, and these are our target qubits. This is a U gate, okay. And you could have n of these qubits, for instance. And so we'd represent it in the same way. We'd put this dot over here to indicate that this is the control, right? And so we'll write this as the controlled U gate. Okay. And another way to write down the controlled NOT gate, rather than putting this cross symbol, so let me see, let me just try to copy it if I can. This is my NOT gate. Another way to represent this is that in we can write it like this, right? So it's basically a controlled X gate. Okay, so you'll find these different representations when you read papers, or you work on some algorithms and so on and so forth. All right, so it's important to know, right, that these two are one and the same thing. Okay, then the next naturally there has to be a symbol for measurement also. And that symbol is as follows. We have a line, a box, an arrow like this, right? So this is that pointer symbol that I had talked about, like this. And then there are two lines coming out of here, okay? And so whenever you have a double line like this, so this is a qubit, it's a quantum bit, and now this is a C bit, okay? Because what has happened is, right, you have measured your quantum state and you get some information, but now that information is in a, well, it's classical, right? Now, one of the most common operations in computation involves the following, right? Copying information, right? So I mean, whenever we transfer some data or what we are doing is we are information is being copied from one location to another location, right? But in quantum mechanics, there is something very interesting happens, which is called the no copying theorem. And this was first proven back in the 1980s by voters. Okay. So what would it mean to say that I can copy a quantum state, right? So it would mean the following, that I have some input state, let's say X, okay, and then I have some target qubit, and I want to copy the state of this qubit, this first input qubit, onto the state of the second qubit. Okay, so what I want is that I should have my original copy, which comes out in the first qubit, and then the second qubit, I should get the same state. Okay. So now, how can I make a copy, right? Well, if you have this thing, so let's say this is, if I initialize this in the 0 state, okay, and now this is a classical circuit. I should mention that. So this is a hello, can you hear me?
Yes, sir.
Okay, I don't know what happened. My Zoom disconnected in my laptop. This is something that's happened many times before, right? So all right, so there was a bit of a snafu there. Anyways, so this is a classical copying circuit, right? So you are sending in some information X, and it is getting you're making a copy of this, right? So now one might think that is it possible to do the same thing with a quantum CNOT gate? All right. So what would be the expression for a quantum CNOT gate? It would look like this. You would have some input state psi, right? You would have some unitary operator, and then both of the qubits would have the state psi, right? And here we'll put the 0 state. Okay. Now let's write. It's some superposition of 0 and 1, right? Now we are working with a quantum state, right? So our input state is psi tensor 0, right? So we can write that as A00 plus B10. And our output state is psi tensor psi. Okay. Now, if I take psi tensor psi, you just take this object and multiply it out by itself. You'll get A square 00, B square 11, plus AB. These two are not the same, right? So you can't just write that as 2AB something. And now right. So this is our input state. And if this is input state, right? So we apply a CNOT gate, and we can ask, I'll let that be a U, and copy this, and you can see that I'm copying all the time, right? And the reason I can do this is because this is all classical information, copy of a quantum state. And so this is A0. So when you apply the CNOT gate, right, what does the CNOT gate do? If this is your control qubit now, remember, right? And this is your target qubit. But what we are trying to do is we are going to copy the control qubit. We're going to, well, hope that we can do that. Okay. On the other end, right? So the input state is this guy. It's the tensor product of psi and 0. What is the output going to be? Well, what happens to 0, 0? Nothing happens to 0, 0, right? The CNOT gate doesn't do anything to that. What happens to 1, 0? It becomes 1, 1. Right? So this is the result of CNOT acting on our input state with the 0 qubit as a target. And now we can compare what we get from the CNOT, right? This is what we get from the CNOT, and we can compare that to what we expect to get if our state has indeed been copied. Okay, and this is not really a proof of no copying. There is a proper proof, and we'll go over that next time. It's actually very simple. Doing is we are just, going by analogy, that you can make a copy of a classical qubit with a classical CNOT gate. So is it possible to make a copy of a quantum qubit in the same way? Right. So what we end up with is that these two should be equal to 0. These two should be equal to each other, right? And the only way that these two can be equal to each other is that, right? But if A or B is equal to 0, then which means that either A is equal to 0 or B is equal to 0, right? And if, well, if we choose B to be 0, let's say, then what is the input state? The input state is A00. And what is the output state? The output state is going to be, well, A square 00. Okay. So again, there is no copying that has been done. And this A square also, well, we'll have to worry about that. And similarly, if A is 0, then psi in is equal to B11, and psi out is equal to B squared 11. So if you have a general state, right? A general state, an arbitrary state, has both A and B non-zero. And so this is very simple. So this is actually, let me use the correct. This is called the no cloning theorem. You cannot clone a quantum state. Okay. So let's see. In fact, we can prove this, and let me go over that proof. Okay. It'll now. By the way, some of you have to leave right now. Who has to leave? Does anybody have to leave? Am I audible? Can you guys hear me?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir, you're audible.
Okay. No, because I mean, I don't want it right, and it's not even being recorded or being heard by you. And in that case, well, I would feel more stupid than I ordinarily do. Okay. Since nobody is saying anything, let me cover. And the reason I'm covering this proof is, first of all, because it's pretty straightforward. And secondly, because it shows a very essential aspect of quantum mechanics, which is that quantum information is fungible. These days, you might be aware that there is this trend going around of something called NFTs, non-fungible. What does the T stand for? Anybody remember? I don't remember. Non-fungible something.
token. Non-fungible token.
tokens, right? And it's I mean, from what I can make out of it, it basically looks like a big scam, because because it's saying that you can own an NFT of the Mona Lisa, uh, but you don't actually own the Mona Lisa. So you in fact don't own anything. Anyway, so NFTs have some applications, but not the ones that are being currently promoted. But the point there is that those tokens are non-fungible, right? Fungible means that there is some mechanism in place to ensure that you cannot uh, alter the association between that token and whatever it is linked to, such as quantum information. Similarly, is non-fungible, right? So if you have a channel, if you have a quantum channel, okay, and this is a quantum channel, Alice and Bob, okay, let's say there is an eavesdropper who's trying to. So how would this person eavesdrop? Right? There is some state psi, let's say, that Alice sends to Bob. What would be required? There would have to be some copying element, right? There would have to be some copying circuit that the eavesdropper installs right here, right? In between this channel. But what the no cloning theorem says is that no such circuit is possible. Right? So it is impossible to make a copy of an unknown quantum state, right? Because to begin with, the eavesdropper does not know what this state is, right? So for the eavesdropper, this is an unknown quantum state, right? So if the eavesdropper tries to make a copy, what will happen is that this state will also get altered, okay? And so Bob will, assuming that there is some other channel through which some verification or some auxiliary information can be sent, Bob will be able to compare the state that he receives from Alice with that auxiliary information and come to the conclusion that something has been tampered with, okay? And so what we want is the following, okay? We have a copying machine, right? And it will be some unitary operation, presumably. And we input some state psi, which we want to copy, right? And what we want is that the output should consist of 2 copies of psi, like this, right? The state is psi, right? And we want to act to get psi tensor psi. Okay. So now let us assume
Hello, sir. Hello, sir.
So you're not audible.
all right. So from what point was I not audible?
So giving S as input and trying to get psi cross.
Okay, great. All right. So what we want is right? That there should be some unitary operator which gives us a result. So let us assume that there are two pure states, psi and phi, for which there is such an operator, right, which does this job. So we would say that U acting on psi tensor S is equal to psi tensor psi, and that U acting on, on phi tensor S, right, is equal to phi tensor phi. Okay. So now let us take the inner product of these two equations. Okay, so this is 1 and this is 2. So I take the inner product of the left and right hand sides respectively. When I take the inner product, what I have to do is I have to take the adjoint of this expression, right? So when I take the adjoint of that expression, what do I get? Let me write it out a little bit slowly. So I want the adjoint of this expression. What do I get? Well, I get the adjoint get psi tensor the adjoint get S, all acted on by U adjoint, right? But since U is unitary, then the adjoint must be equal to the inverse, right? So this is psi adjoint tensor S adjoint acted upon by U inverse. And now I take the inner product where this is one side of the expression, and this is the other side. Okay, so this is the inner product of the left hand side. Left hand side inner product. What will I get? Well, this will just give me the identity, and then I will get the inner product of psi with phi and S with S. Okay, and again, this is 1 taking S to be normalized. So the inner product of the left hand side gives me psi phi, right? It's pretty cool, right? What about the RHS inner product? So the RHS, I take the adjoint of this and the adjoint of, so what is that going to be? Well, it's going to be adjoint psi tensor adjoint psi, inner product with ket phi tensor ket phi. Okay, and what will happen? Well, when you take these inner products, this will be the way in which you do so, right? You would contract, you can only take the inner product of the first Hilbert space with elements of the first Hilbert space and the second one with the second one and so on. You can't mix them up. So this would give you the inner product of psi phi squared. All right. And so the result is that if you compare the left hand side and the right hand side, you get that psi phi is equal to psi phi squared, right? Or in other words, x is equal to x squared. Now, what are the solutions of this? One is x is equal to 0, and the other is x is equal to 1. Okay. Now, when x is equal to 0, what does that tell us? that the states are orthogonal. Okay, and if the states are orthogonal, that means a copying process has failed, right? Because a copying process should produce a state which is the same, right? And the other option is that x is equal to 1. The other option says that phi is equal to psi. Copy failed. And this is a contradiction to our initial assumption. What is our initial assumption? The initial assumption, is that psi and phi are two different pure states, two distinct, we should say two distinct pure states. Distinct means that the inner product is not zero, right? So if x is equal to 1, this is a contradiction to our initial assumption. And let me again correct myself once. If these states are orthogonal, that means that we can only clone those states which are orthogonal to one another. Okay, so the statement is the following. Only orthogonal states can be cloned, right? But now I can always take some state which is a superposition of these two, right? And this is not orthogonal to either phi or to psi, right? And so we cannot clone it, right? So which implies that no general cloning is possible, right? You cannot clone an arbitrary quantum state. And this is a very, very fundamental proof, which was first given by Wouters. Okay.
Sir.
All right. So I'll stop here for the day. Yeah.
So this proof says that there are some general states which cannot be cloned, but like this does not say that there might be some states which can be cloned, right?
Yeah, no, that's right. That's right. So this is saying that a general quantum cloning device is impossible. Okay. But yeah, okay. Your question is your point is valid, that this does not say that some particular states might, but the whole point is that if you come back to this picture again, this eavesdropping picture, right? The thing is, this eavesdropper doesn't know what that state psi is, right? The whole point of this person listening in to some communication is that that person doesn't know what is being said between the two parties, right?
So, but if say this eavesdropper is fine, but if in case instead of the eavesdropper, Alice itself wants to make a copy of the thing she's sending to Bob. So she might probably be able to.
Yeah. If you have a known quantum state, well, then you can always make copies of a known quantum state. Why? Because you know what that state is, and you have some way to prepare that state, right? So, for example, if I want to what's the word? I want to put I have two electrons, and I want both of them in this to be in the spin up state, right? I can always have a device which sends in the electron, like which has some kind of polarizer, so that only electrons with the up spin come out on the other end. But the point is that what is not possible. So what I'm doing here is I am creating two copies of the same state, but I'm not copying one state to another state. Do you understand the difference?
Yes, sir.
So basically, it means that the no cloning theorem says that the superposition cannot be cloned.
Yeah, I mean, an arbitrary state cannot be cloned. And
but a classical state can be cloned.
So this, huh?
But a classical state like 0001,
yeah, of course.
Be
I mean that's what is happening. I mean, if that wasn't the case, then we wouldn't be able to have communication of this form, right? Because the state of my whatever sound is coming out, that's coded into something, and then it's transmitted. And so but again, so yeah, it's important to keep in mind that there's a difference between state preparation and state cloning. You can always prepare an infinite number of copies of the same state, right? But you cannot take an arbitrary state from one system and you have two systems which are the same, like in the sense that both are electrons or both are Josephson junctions or squids or whatever it is, and then transfer the state or make a copy of whatever is the state the first system is and transfer that to the second.
So just to make it clear, like so no cloning theorem states that an arbitrary state cannot be cloned, but there might exist some state which can be cloned. In the sense, it's not arbitrary. There might be a
okay. So that yeah, I will. That might be the case. I don't know. Okay, so I leave that because I don't know the correct answer to that, so I won't say anything about that. Right. So I'll leave that open. Yeah, it is possible that you could clone known quantum states.
So like if the quantum states are known, then like isn't it like classical then?
No, not at all. No, not at all. Not at all. Because you so okay, so this is important. Let me try and answer this question. Okay. What Rohan is asking is the following, that if I know what state the system is in, does that make the state classical? Right? Well, the thing is no, because I can always take my system with the known state and I can have it interact with another system which may be in a known state or an unknown state, right? And I can end up with an entangled I can end up with the two systems being entangled with each other, right? But I cannot take a classical bit, right, of which I know the state, and entangle that with anything else. You understand? Hello?
Yes, sir.
Huh?
So I didn't understand.
So I can, okay, so all right. So I have a known quantum state. Okay, so I can always prepare like some electron or some photon in some spin up state. Okay, but now there are two things. The first thing is that I know what the state is right after it's prepared. Okay, so this is my state preparation machine. Okay, this is my state machine. I give it some raw materials, right? And it always outputs these copies of the same state. Now the point is that the moment the state comes out of that machine, what happens? It will start to evolve, right? I mean, it has been evolving all along. What the state machine is doing, it is taking some arbitrary states, right? It has been taking some arbitrary states and it is evolving each state into the up state. But now, as soon as it comes out of this state machine, there are two things, right? One is that it can interact with other quantum systems. And that is a controlled interaction, right? But it can also interact with the environment, right? So let's say that, well, there is no interaction with the environment, but I can always take some other state, and let's say now my second state is in the down my second system is in the down state, and then I perform an interaction between these two. So I'll represent that interaction like this. Okay, something happens here, and then what comes out of this interaction, right, is something like this. Okay, so what goes into the interaction? This is the input. And what is the output? The output is this, right? So this is an entangled state, right? Rohan?
Yes, sir.
This is an entangled state. Now, I couldn't create this entangled state in the first place if my state was not a quantum mechanical, if my system was not a quantum mechanical system, right?
Yes, sir.
Right? But so the thing is, it continues to be a quantum system. Now the thing is that if it interacts with the environment and undergoes decoherence, right, in that case it will become effectively classical. But if I don't allow that interaction, then it will retain its quantum character. Okay, anyways, see, this is the thing, is that like, you know, you guys should read the textbook also, because a lot of these things are clarified there. Any other questions? All right, then I guess I'll stop it here for today. Okay.
Sir, so like if you know the quantum state, then like you can definitely like produce more and more copies, right? Like as you
No,
told,
so
you
okay,
have the state
so
machine.
the thing is that, first of all, if I give you a system and the system is in an unknown quantum state, right? How can one determine the state of that system? Right? How do you map the state of how do you map an unknown quantum state? And it turns out that this involves a very this is something very, very non-trivial, and it goes by the name of quantum tomography. right? So it's a subfield of its own in quantum information. So assuming that you can map out the state, and create a tomograph. Now, again, you cannot map any quantum state perfectly, okay? Because if the state is big, if the state of the system is, if you're talking about some complicated system, right, the more complicated the system is, the more difficult it is to map. For a simple system, well, yeah. So I'll have to do some reading about that. I'm not sure what the exact answer is. But the point is that it is in general very difficult to take an unknown quantum state and make a copy of that. I'll leave it at that. Okay. All right. So I will end it here.
So one more small doubt.
Go ahead, Rohan.
Yes. So like, so can you just show that eavesdropper diagram?
Sure.
Sir, in this, my question is that, like, what is the difference between Bob and the eavesdropper? If Bob has to know the state beforehand.
No. So the
itself,
different.
right?
So what is happening is that if there is no eavesdropper, right, then there is some channel between Alice and Bob, and Alice uses that channel to send the state to Bob. Okay. And we'll talk about how this happens. This is known as quantum teleportation. Okay, we'll talk about that in the next class. But if there is an eavesdropper, the eavesdropper does not want Bob's reception to be interrupted, right? The eavesdropper wants the quantum state to go through to Bob, but wants to make a copy of that state using whatever some blank device he or she has, right? So you're taking a single state and then branching out 2 copies of that. That is the difference. You understand?
So like, does Bob know the state here then? Like, so like, if like, does this say that Bob knows the state phi beforehand itself? Like, if he doesn't know the state beforehand, like, how can he decode it then?
No. Okay. And now we are just going around and around in circles. I will leave this to you to sit down and do some reading. Okay. And I will end it for now. We'll continue talking about quantum teleportation and so on in the next class.